I'd like to talk about phase changes now, adding in another variable, and that is the variable of pressure. So, pressure is really a measure of the frequency and the force that gas particles are hitting a container wall or a surface, like the surface of me or this table. And so, right now, I'm at atmospheric pressure of 1 atmosphere because I'm at sea level here in Seattle, and that means that we have like a certain rate of gas particles hitting us. As I go up to Denver, the pressure of the air in the atmosphere is going to decrease because I'm higher up. And if I were to somehow go lower than sea level, the pressure would increase. And that's thinking about just the gas and the air around us. But anything that's going to be in the gas stage, if it's in a vessel, will have a measurable pressure. And I'd like to think about supercritical carbon dioxide in the context of this. So, first, I'm going to show you a new type of phase diagram. Before, we were looking at heating and cooling curves, and those are great at showing the temperatures at which phase transition takes place. Uh, so, like for water, it's at 0 degrees Celsius, it freezes, it's 100 degrees Celsius when it boils. Now, those temperatures are going to change if the pressure increases or decreases. And so, if the pressure goes up and up and up, then we're actually going to see an entirely different point in with which this happens. And so, these phase diagrams like this show temperature versus pressure and tries to show what the phase transitions would take look at like at different pressures. So, in these, so here's the phase diagram of water, and then we'll look at carbon dioxide. We've got temperature here on the bottom, and we have pressure on the y axis right here. This one's in torr. Pressure units are usually atmospheres, torr, psi, like pounds per square inch is one. Weather pressures are usually reported in bar or millibar. So there's a lot there's a lot of units out there about it. Pascals. Anyway, I can keep going. So what we're seeing here is atmospheric pressure. So like 1 atmosphere here, sea level is the same as 760 torr. So this is the kind of at where we're at right now. So this is would be the pressure at sea level. And at that point, we have our phase transitions that occur. And so these are labeled as solid, liquid, and gas. So we've got gas down here, liquid here, solid here, and that's typically where they're like the left hand side is usually the solid, the lower part, and to the right is gas, and the liquid's kind of in the upper right hand corner. So within these lines that are separating our solid versus liquid or gas phase, these lines are representing the temperature that phase transition takes place at. So you could take any temperature and pressure and see if a material was a solid, a liquid, or gas, or if it would be in the middle of a phase transition. So my water at like -30 would be somewhere down here, right? And at atmospheric pressure, I could come up here and be like, oh, well, it's definitely going to be a solid at -30 degrees Celsius. But at 0 degrees Celsius, it'll be on this line right here. And that's going to represent a phase transition between solid converting into liquid and liquid converting into solid. It's called a fusion curve. Fusion is another word for melting. It's like the old fashioned way that we called it. Instead of melting point, it'd be fusion point. Similarly, if I looked at water at 200 degrees Celsius, somewhere around here at atmospheric pressure, I'd be like, oh, wow, it's definitely a gas. It's just a whole bunch of steam. But if I did it at 100 degrees Celsius, I'd fall on this line right here, separating the liquid and the gas portions of this chart or this diagram. And so it would be in a phase transition where liquid was being converted into gas or gas was being converted into liquid. There's a fun point on here I'm gonna point out, it's my favorite one. It's right here. It's called the triple point. At the triple point, all 3 phases exist at the same time. So your solid, liquid, and gas all exist at the same time. What this looks like is, let's say it's water, right? It would look like a glass of ice water with chunks of ice and liquid water that was boiling. And so it takes quite a bit of control of the pressure and temperature to hit that point. And it's just in a very specific like combination of those two variables. But yeah, it looks like boiling ice water. It's crazy looking. There's another really important point on this too, and it's called the critical point. It's up here in the right-hand corner. The critical point is when you start producing supercritical fluid. And so it's at temperatures above this and pressures above this point. And a supercritical fluid is something that has properties of both a liquid and a gas at the same time. It's not plasma, that's something totally different. It's just this, it's not one or the other, it's both, and it's at the same time. It's super weird. And so this is it for water, but let's look at carbon dioxide. Carbon dioxide is something that's used quite a bit in the cannabis industry for extractions. And we'll actually talk about that extraction process more later on in the quarter, but we're going to introduce it now, and we're also going to work on it in the lab. So here's the same phase diagram that we just looked at for water, but it's specifically for carbon dioxide. And so the temperatures where the triple point or the critical point are different. And also you can see the lines are different as well for the transition points between solid and liquid, or liquid and gas. So here the scale is also important. So about 1.01 bar, and so sorry, these are different units because all of these graphs are, everyone has a favorite pressure unit, is sea level. So where we're at right now in Seattle. So this one is going up to really high pressure. So it's very much a different scale. So right now, if you were, and it's starting at a temperature at 200, it's marking it in Kelvin. So 0 degrees Celsius is somewhere around here. And room temperature is going to be kind of around, yeah, it's kind of around here. And like 100 degrees Celsius would be around here. So you can see that at 1 atmosphere, carbon dioxide is going to exist as a gas, right? So to have solid gas at that point would mean it'd have to be very, very cold. And so I can go to the grocery store and I can buy solid carbon dioxide. It's called dry ice, right? I'm not going to touch with my hands, but I'd be really careful with it because it's super, super cold. It's way colder than just ice because it's going to have to be somewhere down here. So if this curve extends, it's going to have a really low temperature to be solid at just normal sea level atmospheric pressure. So we have to keep it really cold, which is why it's stored in a freezer. And like, even if I just put it in my freezer at home, it's gone pretty quick in a few days. It is fun to play with. So thinking about carbon dioxide, here is its supercritical fluid like segment of the graph. And so you can see that at about room temperature, we can reach the critical point, that critical point where the liquid and gas kind of start acting in the same way. But we have to do it at pretty high pressures. We can do that by putting in a vessel that restricts the volume, and pressure will build up and it'll get higher and higher and higher until you have a supercritical fluid. So we just need to put carbon dioxide under pressure at pretty regular temperatures to make it a supercritical fluid. And the thing that is so interesting about carbon dioxide as a supercritical fluid is that it is a non-polar molecule, if you remember. So we've got carbon double bonded to 2 oxygens. So it's non-polar, it's super small. And if we can control its pressure, we can increase its pressure and it becomes a liquid. And then we just bring it back to normal sea level pressure and it's just a gas and it just kind of like goes away. And so this actually makes a really good solvent, and we'll talk about its solubility properties next week. But I want to introduce it as a phase that's used in extraction now. Um, and so here's what I like this picture because it kind of shows what it looks like. So a supercritical fluid will have both the properties of a gas and a liquid. And so here, this is a window into a pressure chamber. You can see here at just like normal ambient pressures, we have both a liquid and a gas present of our carbon dioxide. You could see a line that represents, oh, we've got liquid, we've got gas. And then as we increase the temperature and the pressure of this system, you can see it really changes until we hit this phase here where there isn't a difference between the liquid and the gas. And what we have is our supercritical fluid. And so it's denser than a gas, but it's less dense than a liquid. And it will have properties of both the gas and the liquid. Super cool. And it makes a fantastic solvent, which we'll work on that vocabulary later, but it does a fantastic job of extracting nonpolar compounds from plant material and separating them from the rest of the plant. And so it's used in cannabis extractions, it's used in essential oil extractions, it's used to decaffeinate coffee. It's fantastic. And so we will spend more time later in the quarter talking about supercritical carbon dioxide extractors that you might see in cannabis labs. And they're usually these pretty large setups just because you're processing a lot of material. And so, like, here's an example of one of them. We'll look at a few of them later. And the way these are working is they really have a space that is compressing our carbon dioxide to be supercritical. And then it is going to pass that supercritical fluid through our plant material. And then it's going to have the supercritical CO2 and then also the extracted oils and cannabinoids from it that we can then separate. And then we can just have the extract from the plant. And then we can take that carbon dioxide and either release it into the atmosphere or just recycle it back into the process. And so we'll talk about this more, but I wanted to share it because we're talking about phase transitions, and supercritical fluids are really just part of our phase diagrams. And it's a state of matter for our compounds that's kind of in between two of them, the liquid and the gas.